We are start the second session of our keynote speaker. So I have the pleasure to introduce today's keynote speaker, Robertas Damaševičius, which is the expert in AI technology and working on the edge between the medicine and AI, trying to find a new applied of IT in the brain cancer research. He's working for few different research institutions. I found the information that he's working for Department of Software Engineering of Kaunas University of Technology, also for Department of Applied Informatics in Vytautas Magnus University, and also in Poland in Silesian University of Technology. Today, Professor will show us concept of AI-driven innovation in brain cancer research. So, Professor, the floor is yours.
Okay, thank you for inviting me to make this keynote speech. I've been involved for many years with FedCSIS as a conference speaker, participants, and I'm happy that today I can participate in the role of a keynote speaker, and I'm thankful to the organizers for this opportunity, and I hope that this keynote speech is somewhat also related to the previous keynote speech, both in general, because it is concerning the application of artificial intelligence methods, but some topics also like black box AI and explainability of AI also may be related to other fields such as business informatics. So today I will discuss the recent developments in artificial intelligence methods for brain cancer research, and covering different kinds of methods, different kinds of architectures which we have proposed recently. But first I would like to start from the motivation why this research is important. Basically, the brain tumors is a kind of disease which is caused by the abnormal growth of tissues in the brain, and the incidence of this disease is growing annually in the world, and the statistics mostly focuses on the developed countries, but also in the developing countries this disease may be not so easy to recognize due to lack of experts, due to lack of medical equipment. But what is specific is that once diagnosed, it has a high level of mortality. It's difficult to treat, so that's why it is important to diagnose this disease as early as possible, and that's why the role of artificial intelligence methods is important for early recognitions of brain cancer. So basically today I will focus on the most prevalent, most important applications of artificial intelligence methods in brain cancer. So first of all, for classification of tissues and tumors. So the most simple case is binary classification, when you aim to recognize healthy tissue from the malignant tumor tissues, and once you identify that a person has a tumor, the next step would be to recognize what kind of tumor the person has and how high grade is the tumor. Of course, the low-grade tumors are more easily to be treated, and high-grade tumors, they have a low survivability of the person, of a patient. Another task is to perform tumor segmentation, so correctly identify the boundaries of the tumor, and this is important in case of operations, because the surgeons they need to plan the operation. They need to know exactly in which part part of a brain the tumor is located, and that's why it is also important. I also will cover extensively the problem of explaining the result of deep learning models, artificial intelligence models, because it's not enough you to know the decision of a model, to know the prediction of a model, due to various reasons, due to legal requirements and other requirements, because you need also to explain why the model has taken one or another decision. And also other applications are prevalent beyond image analysis, such as survival time prediction. So once you know information about the location of the tumor, its volume, its age, you can try to estimate how much time the person has to live after the diagnosis time. So first of all, some basic information about the input data which models use in these tasks. So basically, the common inputs of artificial intelligence models which are used for brain tumor classification are images which are obtained from magnetic resonance imaging, so MRI scans, and there are several types of these images depending on how this equipment is used and how the magnetic resonance interacts with the tissues and how it is scanned. So it's details, and other type of clinical data also can be used in order to supplement this information which can be extracted from medical images in order to improve the accuracy of performance of a model, such as, for example, making use of demographic information, medical history, and other medical data which is available in the patient's file. In some cases also so-called histopathological data is also used. So when a biopsy of the tumor is taken and it is analyzed, and the molecular level and on the chemical level, this data also can be used to supplement the information which is obtained from the analysis of the images. But today I will mostly focus on the analysis of the images, because this is what our research group does in this research topic. And the outputs of such models are usually the tumor type. So it could be just a simple decision if is the patient healthy or is he diseased. In case of multi-class classification, it would be the identification of the specific type of tumor which is present, because different types of tumors, they can have very different texture, very different location and boundary. It is not so easy to recognize different types of tumors, especially since there is still a lack of reliable data which can be used to train the models. Also, it is important to recognize or to predict the grade of the tumor based on the image, because higher grade tumors, they have a higher level of aggressiveness, meaning that there is a larger threat to the person's life, and the survivability of such patient may be lower. in order to assess the reliability of this prediction, often confidence scores are outputted as an additional output in order to indicate the likelihood of a tumor belonging to a certain class, because in some cases the model is not able to reliably assign the observed tumor to some specific class. So to overview the recent evolution of deep learning models for brain tumor recognition, I made a timeline which represents the recent achievements and recent innovations in this area. And you can see that this timeline is rather short, representing a very rapid evolution as regards to this area of research. So basically up to 2020, you can call them traditional or convolutional neural networks were used, which also were used in for other tasks of biomedical imaging. And they usually have indeed strong results in classification, in segmentation tasks. However, they are not so much successful with brain tumor recognition tasks due to complexity of recognizing this type of tumor, as opposed, for example, for in case of skin cancers, because in case of skin cancers, it appears that it is a more easy task to recognize. And here, since we are dealing with magnetic resonance images, they themselves have various issues related to the noise, to the blurriness of the image, which requires adoption of more complex methods, adoption of more innovative methods. And after CNNs, the field has moved to using so-called vision transformers. So transformers, first they appeared in the field of natural language processing, and they also played a prominent role in developing various kinds of chatbots, for example. And also the transformer architecture was adopted for analysis of images, in particular medical images, so it's called vision transformers. And they specifically can capture long-range dependencies in the images, meaning that you're not looking only at the local context of the image in order to recognize the disease, but you can also look at some dependencies between different parts of the image, and in this way you can extract more relevant information from the images. So these architectures have evolved beyond original architectures which focus, for example, on two-dimensional brain images towards three-dimensional brain images, because when the brain is scanned, you can obtain the image of the brain at different layers, different slices, and when these slices are all combined, they result in the three-dimensional or volumetric image of a brain, which of course has a more comprehensive information about the brain than just taking a single slice. And the most recent achievements in this area, they focus on combining multimodal information about the brain, so combining different types of scans using different equipment, different technologies, and also integrating it with explainability, so that you could or the clinician could understand not only is the brain impacted by the brain tumor, but why the specific decision was taken, which feature of the data had the most influence on the decision of the model. So then typical convolutional neural network is used to analyze brain MRI images. They work in fairly conventional way, in the same way as, for example, convolutional neural networks are used for such simple tasks like recognizing cat images from dog images. So these networks, they have a hierarchical structure consisting of multiple convolutional layers, each of which layers successively extract different features of the image, starting from low-level features, which in case of a brain could be various edges and textures and contrasts of various brain areas. Then successively the CNN model extracts higher and higher abstraction of features such as various shapes, structures, and ending with various tumor regions and anatomical features which could be identified in the MRI scans. So the result could be various fine-grained features that allow to differentiate in the final layer between healthy and abnormal brain tissue. So you can see here a typical workflow of brain tumor classification. So as I mentioned before, this workflow starts with input brain MRI images, which are used to train the model. And of course, first, in order to use these images, you need to pre-process these images in order to remove the noise, remove the blurriness, and usually some kind of image filters are used, such as median filter, which help to improve the image quality, and this of course is positive for overall network performance. Since the brain images, they have the complete view of the brain, you can try to make the network focus on the specific regions of interests, which can be identified, for example, by the clinician, or the network itself can identify these regions of interest. And in this step also you can apply various methods such as clustering, for example, in order to cluster similar pixels and similar areas of the image together in order to pinpoint the areas in the brain which are more likely to contain tumors and later focus only on these areas. Next, the next step is feature extraction. I already covered it in the previous slide, so this is done by the layers of the convolutional neural network. One thing to note that in order to improve the performance of the model, also it is beneficial to optimize the model, optimize the hyperparameters of the model, and this can be done using various optimization methods such as heuristic optimization method. And then the trained model can be used to recognize, as in this case, abnormal tissues from the normal tissues. Another related task is localization of the brain tumor by image segmentation. It's different from the previous task because in this case not only the model learns does the brain has the disease or not, but it tries also to pinpoint the specific location of the diseased tissue in the brain. And this kind of information is very, very useful because it first of all can provide better understanding of overall brain structures, but it is also important for accurate diagnosis and treatment planning, and also for monitoring the progression and evolution of the disease if the person is scanned regularly at some time intervals. And the task is not so easy because, as I mentioned, brain tumors have many different types, and they can vary greatly in shape, size, and appearance. So basically it is difficult to generalize and find some commonalities between these different kind of tumors. They have a great degree of variability. So to train the models effectively, basically you would need to have a very large amount of data collected from patients, which is in many cases difficult to collect, difficult to obtain. So that makes the life of the AI researchers more difficult. And of course, if such solution is implemented, it would allow to automate tumor segmentation, because currently the doctors do it manually, and this work is labor intensive and it is time consuming, and it may lead to inconsistent results, meaning that different doctors can have different opinions on the same image via the boundaries of the tumor, for example. And if you're looking just at the work of one doctor, it can be very difficult to reconcile the results of manual segmentation with the work of another doctor. So the inputs for the models which do brain tumor segmentation is almost the same as the inputs which I covered for the classification task. So it includes both images, but also can include additional information such as demographic information. And the output of brain tumor segmentation is first of all, the regions of the brain, which are usually represented using the colored map, as you can see on the slide, which delineate or emphasize the tissues which are more likely to be affected by the brain tumor disease. And additionally, the trained model can output quantitative metrics such as estimation of the tumor's size, area, volume, shape, which are important for diagnosis and are helpful when medical doctors must adopt some clinical decision. So, in order to perform this task, you can use purely artificial intelligence models based on deep learning models, but you also can combine it with some fairly classical computational methods such as fuzzy logic. In this case, you will get a hybrid intelligence, which also was covered in the previous keynote. In that case, when, for example, a fuzzy logic is used, you can benefit from the advantages of the fuzzy logic to handle the uncertainty and imprecision in the original data, when you need to identify the boundaries between tumors and healthy tissues. As in the paper which was published by by my research team, we adopted fuzzy logic specifically to locate the tumor edges in MRI scans. And fuzzy logic allows the system to make more nuanced decisions when the aim is to detect the edges and boundaries of the tumor in order to take account into so-called partial truths when it is difficult to correctly delineate between healthy tissue and the malignant tissue. So it doesn't follow the strictly binary logic. If we consider the steps which are used in this method, some of these steps are fairly standard, like first of all to improve the contrast of the image in order to make it more clear for the network. And then you can adopt the fuzzy rules which can be used to detect the edges in the image and use this information as a set of features to as an input to the convolutional network, so that convolutional layers can learn to extract this information about the about specific features of the image or neighborhood of pixels, which can contain the diseased tissue. And then fuzzy inference converts back this information in order to detect the edges. So in terms of applications, such hybrid methods which combine strictly deep learning methods with some traditional computational methods such as fuzzy logic, they can be of greater benefit in this case because of the fuzzy nature of the problem itself. I already mentioned that to go beyond the current state of the art, which uses single type of MRI images, the next step would be to combine or integrate classification and segmentation tasks by performing multimodal analysis of brain images. And by multimodal analysis, I mean using different modalities of MRI images. So the aim is to get as much information as possible from the available data, and in many cases when the scan is performed from different angles using different types of MRI scan, this allows to extract more comprehensive information from the brain, leading to more reliable and accurate decision. So here you can see the typical workflow of such multimodal MRI image analysis and feature fusion, and you can note that as an input to the deep learning networks, they use different types of brain images which can be used to train several different networks, and the output of these networks can be combined using, for example, ensemble learning or feature fusion in order to get a more comprehensive information from these images. And the final step could be using optimization methods to select the best features extracted from different types of images, and the decision can be taken by a simple machine learning classifier, which performs feature classification for final decision. So the typical output of brain image segmentation, you can see it on the slide, it can be represented as a so-called segmentation map, which could be binary, or it can have several different classes colored in different colors. And the aim of the segmentation map, you can see it in the third column of this figure, is to pinpoint the specific area of the tumor, which the model believes that it contains a tumor. So basically it provides the visualization of tumor size and its shape for the clinical diagnosis. And additional information also can be provided, such as specifically outlining the boundaries of the tumor, which in the fourth column of this image shown in the red color. And this information is particularly important in case of neurosurgical operations. So before I proceed to discussing the need for explainability of artificial intelligence models, specifically in healthcare applications and specifically for brain tumor recognition, the artificial intelligence models and products, systems developed based on artificial intelligence models started to be regulated more strictly. And of course, in different countries or in different areas, different regulations exist, which raise different requirements to the AI-based products, specifically in the European Union, the so-called medical device regulation exists, which governs medical devices and diagnostic systems, including AI-based software, like network trained for recognizing brain tumors and used for medical purposes. So it raises several requirements, such as requiring to present clinical evidence, safety validation, and also explainability of algorithms before they could be approved for clinical use. So in the United States, the FDA, Food and Drug Administration, it also, before the algorithm could be applied for clinical use, it requires that the evaluation of its safety, effectiveness, and generalizability and risk management is performed. And specifically, if you would like to apply or use some trained models for clinical use, it is treated as software as a medical device. So it's not like a pure algorithm, but it's some kind of medical device which has the shape of software, and it also covers the models which I discussed in the previous slides. Also, regarding the requirements of GDPR, General Data Protection Regulation, several requirements are raised, and it includes specifically as relates to the explainability of artificial intelligence, the right to explanation. So basically, if a doctor uses some kind of artificial intelligence based tool as a decision support in his work, the patients have a right to demand to know how algorithmic decisions about their health were made. So the doctor must explain the doctor must not only present its decision, but also to explain how it was made. So in order to fully explain it, the algorithm must be explainable. So it must be provide its own explanations regarding the taken decision. So, as regards to the previous keynote, I also discuss the black box problem. And you can see the famous painting, which is called Black Square, which very succinctly represents the problem. So you can look at this black square to see how it looks very beautiful. Maybe it also can be useful. It can tell you something which you do not know. But it actually cannot explain how it works, because you are looking only from outside, but you cannot get inside to understand how it works. So that lack of transparency in understanding how such models work and how they arrive at the decision limit the adoption of artificial intelligence in clinical settings. So basically, if you do not understand how something works, you cannot trust it, because sometimes it may be, for example, mistaken. Sometimes it may arrive at wrong decisions. But since you cannot recognize, cannot understand it, you cannot trust it in all decisions, because how it works, who knows? Also, it is difficult to assign responsibility in cases of errors or adverse outcomes. So who is responsible if a model is wrong? Is it responsibility with the persons who collected data, who developed architecture, who trained the model? Because usually many different stakeholders are involved in this process, and it's difficult to assign or share responsibility between these stakeholders. And again, if such models would be aiming for official approval in order to use in clinical practice, you need to overcome the regulatory barriers, which I mentioned before. So you need to prove that these models are safe to use before they can be actually used. So why AI explainability matters? First of all, you need to have a transparent reasoning so that the patient can understand how AI was used by the doctor and how it influenced the decisions of the doctor, because there should be a trust between the patient and the clinician of a doctor. If there is no trust, the diagnosis would not be useful. As I understand, the patient may not believe it and may not take the medicine prescribed, for example. Also, it is important to reduce the risk of misdiagnosis, especially in the case of life-critical decisions. As in case of brain tumors, where the mortality is really high, so it's really a critical decision, and any error may result in very negative outcome. So that's why it is important to integrate the human in the decision loop. So it's not like just we fully rely on the artificial intelligence tool, but every decision which is taken by the AI must be overseen and supervised by the clinician, which participates in this loop. So that's why it's called human in the loop, in order to provide oversight, so that the doctor, for example, if he recognizes that the model is wrong, could override it and do not allow it to proceed further to the decisions which can have negative impact on the patient, because experts, which have multi-year experience, they can recognize if the AI tool is wrong, and for example, if its decision is based on some clinically implausible features or some spurious correlations which undermine the confidence in this decision. So, to proceed further, there are basically two ways to explain the decision of the model. One way is called post hoc, meaning after. So basically, if you have the prediction of the model, the explanation is generated after the prediction by analyzing the prediction itself. So it can work with any type of artificial intelligence model just by analyzing its outputs. And another way to explain is so-called intrinsic explainability, and it's called intrinsic because the ability to explain its decision is already integrated, already built into the model architecture. So in order to implement this intrinsic explainability, you need to develop custom models which specifically provide capability to explain its decision. So as an example of method which uses post hoc explainability, the method is called GradCam, so gradient weighted class activation mapping, and it works by highlighting important regions in image contributing to the model's prediction. So I will not go too much into details how it works. Basically, it computes additional information during the working of the model, and this information is used to produce a heat map. So a heat map is basically a colored map in which the specific color is used to show the areas which have a higher which had higher influence on the decision of the model. So such heat map is then overlaid with the original image, and it allows to see the most significant regions in the brain image influencing the decision. So basically, it's another way to identify the tumor tissue in the original brain image, because often these areas, they overlap, as you can see, for example, in the lowest row of the example given on the slide. So the tumor in the original image has a white color, white area, and the network has arrived at the decision that it is a tumor, a malignant tumor, and that it shows which areas of the brain image have the most influence on this decision. And you can see that these areas overlap with the actual tumor image. So the practical application of such a explainability method is, first of all, that it allows to see the specific tumor regions within the brain MRI scans, which AI model has flagged as abnormal, and it also allows to enhance the traditional classification methods by adding this localization opportunity. So we worked on improving this method, and our group has suggested an improvement of grad-cam method, which is called xgrad-cam, and it actually extended the standard method by enforcing two requirements, which are called sensitivity and conservation. Basically trying to optimize between sensitivity, which measures the true influence of each feature, and conservation, requiring that the sum of the feature contribution would be equal to the class score. So this requirement prevents that explanations drift away from the decisions of the network, ensuring that there is no contradiction between the decision and its explanation. So if you take two these factors into account, sensitivity ensures the relevance of the explanation. So only considering the features which truly affect the prediction are emphasized, and conservation ensures the faithfulness of a decision and faithfulness of explanation, that it indeed explains the decision what was taken by the model. So here are some of the visualization results, and it uses the same type of heat maps, allowing to identify the areas of the brain which influence the decision. Another method focuses on the intrinsic explainability, and in this case we used attention models in order to enhance the explainability of a network, and specifically here it combines two different types of attention models. Disease attention model filters out irrelevant areas, focusing only on tumor-related regions. And the spatial attention model learns which spatial features across channels are most discriminative for the tumor types. So the network generates the attention maps during the feature learning stage, and these maps can be used to analyze the specific areas of the brain where the network is focusing while taking the decision. So then comparing both methods of explainability, post hoc explanation and intrinsic explainability, they have both strengths and limitations in order to explain the decision of a model. In terms of post hoc explanation, they can be easily integrated with other models, which provides some flexibility, but also it can be considered as a limitation because the explanation is separate from the model itself. In case of intrinsic explainability, the explainability is integrated, is built in the architecture of the model itself, which on one case is good because you get the decision and explanation from the same model, but it also requires more work from the AI researchers, AI engineers when building such models. Okay, so the time is not, we do not have much time. I will cover only 3 state-of-the-art deep learning models, which have been applied recently for brain recognition tasks. I already mentioned vision transformers, which can capture global context across image, which is quite helpful when you need to analyze brain images. Specifically, how we worked to improve the architecture of vision transformers is to integrate it with explainability in order to develop explainable transformers. So additional to the usual architecture, which includes components for patch embedding, positional encoding, and self-attention. The model also has ability to produce explainability heat maps to explain its decision. And our solution, which we called GAT transformer, integrated vision transformers with graph attention networks. And this kind of network allows to explicitly model the relationships between different neural network channels, which helps to find interchannel correlations across different layers, and such information allows to highlight critical channels and allows to produce the explainable importance scores. So this kind of enhancement, this kind of extension of vision transformers allows to generate both prediction and explainability at the same time. And you can see some of the explainability heat maps produced by this method, which allow to identify the tumors more clearly with more fine features regarding the boundary of the tumor, especially in the complex cases when the tumor is not very well localized, but it spreads out in the tissue, having a lot of fine details and different areas of the brain affected. Another recently proposed deep learning models, which also I believe have a very great future for brain tumor recognition, is called MAMBA, and it belongs to the family of state space models, which similar to vision transformers can model long-range dependencies in the image. However, the difference from vision transformers is in the computational cost, because transformers have a quadratic complexity, making them prohibitive to use in case of high-resolution brain images and very large data sets. And MAMBA model, it has linear time architecture, so it can be trained more easily on the large data set of brain images and making it more efficient to compute. So a specific advantage of vision transformers I already mentioned. It's the linear cost, making them more efficient to train and more efficient to deploy. And the solution which we proposed is called NeuroMAMBA, and it integrates MAMBA with explainability in order to derive explainable brain tumor segmentation. And the benefit, of course, if we have low computing resources, if we have do not have high-tier equipment, it's much more easier and much more quickly to train on the available sets of brain MRI images, arriving at the results which are comparable to to using vision transformers. And additionally, it also allows to derive segmentation maps, which are used to explain the decision. And the final architecture, which I also wanted to mention, which I also believe has a great future in this kind of application, is so-called mixture of experts. So basically, instead of one network, you train multiple expert subnetworks, and each of these networks can be used or can be trained to recognize a specific type of a disease. So you train one expert to recognize one type of glioma, another type of expert on another, and then you combine the knowledge using a gating mechanism which dynamically selects which expert should be activated. So in this solution provides additional advancement, innovation beyond current deep learning model architectures, which were not able to account for the complexity of this research domain. So our solution used mixture of experts to train different experts on different type of brain images, essentially providing a multimodal capability for brain tumor recognition. And in case of stage 1 of this architecture, it is trained on different types of images. Stage 1 on T1, stage 2 on T2, and then the final stage focuses on refining and consolidating features and combining the decisions of each expert for the final decision. Okay, so I see that we do not have much time, so I will skip survival time prediction, which is also very important. And deep learning methods also are extensively used. To cover some future directions in AI for brain cancer research, I believe that multimodal fusion, to combine different types of clinical data for decision, is very important and will be addressed by researchers in the future. Also tracking tumor evolution. So it's not like you have just one snapshot of image at some specific time, but it's important also to observe the patient, to see how this tumor develops in order to understand how it can be treated. And also very important thing, which I do not cover, but I think will have a great future, will be digital twin frameworks. So developing virtual twin models of a brain based on deep learning networks, which would allow to personalize treatment for the specific patient. So to conclude my keynote presentation, there is a great deal and rapid evolution in this area, with various new architectures proposed almost every month, focusing on reasoning, focusing on explainability beyond simple decisions. And the most recent models, they also focus on efficiency, because the high resolution volumetric MRI, they are very large data and require a lot of performance to compute. So taking a look at the efficiency is very important. And also mentioned human in the loop, which is very important, that AI is not used standalone, but it should be integrated with the human in the decision process. And I would like to thank my collaborators, my PhD students, both my former students and current students, which of course allowed to achieve the results, because it's not only the algorithm, is also taking time to develop these methods, to try these methods, and without the help of these collaborators, it would not be possible to advance this research. So the final line, which I would like to emphasize, is that the future of brain tumor diagnosis isn't just about the smarter models. We need to trust in these models. And in order to trust, we need to understand how these models work. Okay, thank you. And any questions?
Thank you very much for a very interesting presentation. I have to open a discussion session. It will be very short, only one question, because professors stay with us during the conference, and we can ask the question, because we have planned the family picture in front of our building on the stairs. The friendly drone are waiting for us. So because of battery capacity, we have to be quick. So first, anybody have the question to the professor? I have one. Here we have the question.
First of all, thank you for the presentation. I think not only exciting from the computer science perspective, but also the topic is of very interest of everybody, I believe. I wanted to ask about this explainability in terms of recent popularity of reasoning models. You mentioned, for instance, visual LLMs as one of the versions, and in particularly, what we discussed was more explaining in a strong context of this image segmentation. But you also mentioned this more information fusion with other clinical data. Mm-hmm. So I wonder if you see any applicability of these reasoning capabilities of VLLMs when combined on these more multimodal representations.
Yeah, I think you mentioned very correctly this aspect. I didn't cover it, but large language models, they have a very great ability to explain something which you put. If you would put, for example, brain image, it would be it would provide a very nice explanation why what parts of it has and why it is healthy or why it has a disease. But there is another problem related to hallucination. Because actually we are not sure if this explanation is correct or not. We need a medical expert to evaluate this explanation. So that's why I emphasized the human in the loop. Because human must be integrated in this process in order to check if indeed this explanation is correct. We cannot rely just on the quality or on the niceness of the explanation. We indeed need to be sure that it is correct, and that is still a problem with large language models.
Okay, thank you very much for the question and the answer. Professor, one more time, thank you very much for the very interesting presentation.